Okay, so we've all seen those mind-blowing AI agent demos, right? But here's the thing. Taking that cool prototype and turning it into a reliable, production-grade system, that's a whole different ballgame. It means we have to stop thinking like prompters and start thinking like systems architects. So let's put on our architect hats and really map out how to build agentic systems that are actually built to last.
Here's how we're going to break it down. First, we'll get into why simple agents just fall apart at scale. Then we'll open up the multi-agent playbook and look at the core architectural patterns you need to know. After that, we'll compare the big three orchestration frameworks, LangGraph, CrewAI, and AutoGen, before walking through a super practical checklist for getting production ready. And we'll wrap it all up with the one big idea you need to walk away with.
All right, first things first. We have to understand the huge gap between a demo that works once and an agent that works reliably 1,000 times in a row. With normal software, we worry about loud crashes and obvious bugs. But with AI agents, the biggest threat is way more subtle. It's what we call the silent failure.
This quote from a production failure report just nails it. Unlike a normal program that throws an error you can see, an agent can become a zombie task. The process is still running, the server looks healthy, but inside, nothing's happening. The agent has just stopped. It's a really unique and frankly dangerous failure mode we have to design against from day one.
And believe me, the stakes for getting the architecture wrong are enormous. Get this. Research shows that if you just misapply a multi-agent pattern, you can crush your performance by a staggering 70%. Let that sink in for a second. This isn't some minor tweak. This is a catastrophic failure that comes directly from your initial architectural choice.
So you might be wondering, why can't we just stick with one big, super smart agent?
Well, because they hit a wall, and they hit it hard. Performance just tanks once an agent has more than, say, 15 tools to juggle. Its context window gets totally bloated, turning it into this slow, expensive bottleneck. And the real killer? If that single agent fails, the entire job is dead in the water. That single point of failure is exactly why we have to start thinking in terms of teams of agents.
So, if single agents are out for complex tasks, what's the solution? Well, let's open up the multi-agent playbook. Think of these as the fundamental blueprints, the core patterns that architects use to build systems that can actually scale.
At the highest level, there are really two ways to structure the work. The first is sequential. It's like a classic assembly line. Agent A does its part, then hands the result off to Agent B. It's predictable, it's great for structured tasks. The biggest risk? Dropping the baton. Losing context between handoffs is a huge source of failure. The other way is parallel, which is more like a brainstorming session. You have a bunch of agents all tackling different parts of the problem at once. It's way faster, but now you have the headache of trying to merge all their different ideas into one coherent answer.
And how do these agents actually talk to each other? Well, you've got the supervisor model, which is basically a boss and worker setup. A central manager agent breaks down the problem and hands out tasks. It's clean, it's predictable, and it's easy to debug. Then you have the peer-to-peer model, which is like a roundtable discussion. Agents negotiate directly with each other, no central boss. This is incredibly resilient, but all that freedom comes at a price.
And that price has a name: coordination overhead. In that roundtable or peer-to-peer system, the number of potential communication channels just explodes, quadratically. What that means is with just 10 agents, you suddenly have 45 potential conversations to manage. If you don't account for that, this overhead will silently choke your system's performance as you try to scale up.
And this table right here brings it all together. This is your decision-making cheat sheet. For a simple assembly line workflow, the supervisor pattern is perfect. Its low, linear overhead is exactly what you want. But if you have a problem that needs negotiation and debate, you have to be willing to pay that high, quadratic overhead cost of a peer-to-peer system. The key is to consciously match the pattern to the problem.
Okay, so now that we get the patterns, let's talk about the tools. The big three frameworks today: LangGraph, CrewAI, and AutoGen. They're not just libraries. They are really opinionated implementations of the very patterns we've just been discussing.
LangGraph is built for the architect who needs absolute control. It basically forces you to treat your workflow as a state machine, or more accurately, a graph. You explicitly define every single node, every single edge, every possible transition. This makes it the absolute gold standard for production systems where things like compliance and predictability are non-negotiable. CrewAI, on the other hand, takes the opposite approach. It is all about speed. You use natural language to define agent roles, like you are a senior researcher, and then you assemble them into a crew. It abstracts away all the complex plumbing, which lets you spin up a hierarchical team of agents ridiculously fast.
It's fantastic for rapid prototyping.
And then you've got AutoGen. Its core philosophy is that the best way to solve really hard problems is through conversation. It creates a group chat where agents can debate, negotiate, and even write and execute their own code to prove their points to each other. It really shines on tasks that need that kind of iterative refinement and collaborative problem solving.
This slide really gets to the core architectural difference between two of the giants. AutoGen uses something called an actor model. You can think of its agents as totally independent processes that are just sending messages back and forth. This is great for highly distributed systems where you might need to dynamically spin up new agents on different machines. LangGraph, by contrast, is built around a central, persistent state graph. This is its superpower. It's what gives you durable execution, so if a process crashes, you can resume right where you left off, and it makes adding human-in-the-loop approval steps incredibly natural.
So here's your decision guide. If you need fine-grained control, rock-solid state management with checkpointing, and native human-in-the-loop for a mission-critical system, your choice is LangGraph, no question. If you need to build a proof of concept in a single afternoon, you start with Crew AI, and if your problem requires complex negotiation and dynamic collaboration between agents, you're looking at AutoGen.
Okay, you've picked your pattern, you've picked your framework. Now comes the hard part, the actual engineering discipline required to make it truly ready for production.
In production, you're going to face what I like to call the four horsemen of the agent apocalypse. First, you've got error propagation, where one agent's tiny mistake cascades and corrupts the entire system. Then there's poor state management, where a crash can wipe out minutes or hours of expensive work. You've got expanded security risks because every agent is a potential new entry point for an attacker. And finally, a brutal lack of observability, making it almost impossible to figure out why a 20-step workflow went off the rails.
So how do we fight back? We have to engineer guardrails. Step 1, you must enforce strict schemas on all your tool calls to stop the agent from hallucinating parameters. Step 2, set budgets. You need step limits or timeouts to automatically kill any agent that gets stuck in an infinite loop. This will save you from terrifyingly high costs. Step 3, enforce bounded autonomy. For high-risk actions, like financial transactions, the agent has to stop and get human approval, no exceptions. And finally, for true compliance, you use a state machine like LangGraph to mathematically guarantee that critical safety checks can never, ever be skipped.
All right, let's bring this all home. We've covered the failures of single agents, we've walked through the multi-agent pattern playbook, we've compared the major frameworks, and we've gone through the production engineering checklist. It all really boils down to one central idea.
And this is it. This is the most critical takeaway of this entire thing. Your choice of architecture is the most important decision you will make. It defines the absolute ceiling of your system's performance, its reliability, and its cost. You can spend weeks crafting the most perfect, elegant prompts, but a brilliant prompt can never, ever fix a broken architecture.
So, I'll just leave you with this one question. Your agent works perfectly in the demo. It looks amazing. But is it truly engineered to survive the chaos of the real world? Because the answer to that question is the only thing that will define its success.